So hello, everyone. Can you hear me?
Yep.
All right, great. My name's Zach Fuchs. I'm an assistant professor here. I've been here like a little over 2 years now. Went by pretty quick, actually. Um, my background, I guess, well, I'll just go through that in the slide. I have some of that in the slide. So I'll go ahead and I'll share my slides here. And can you guys see my slides okay? Maybe?
Yes.
All right, great. So most of my research can be broadly, I guess, categorized as control and sensing in adversarial environments. So we're trying to develop strategies for autonomous. These could be physical agents, these could be cyber agents, these could just be sensing strategies for things that go out and live in a world where there's other things in the world with different goals. And we pose these as mathematical games, and we try to solve them. So that's what I'm going to talk about, a couple examples of that work tonight. So thanks again for the invite. I appreciate it. I like talking about my stuff. So any opportunity I get to talk about it, I like to jump on that. So here's an outline of the presentation. I'm actually going to go through a lot of stuff pretty quickly. If there's any questions, feel free to ask questions anytime, or we can talk about it at the end, or you can shoot me an email and we can talk about it offline sometime. But I'll do a little bit of my background, and then I'll go through kind of the research that I do, and then some examples of that research. So my background, I grew up in Southern Indiana. I went to University of Evansville. That's a small university. It's like 3,500 students grand total across the whole university that happens to have a nice engineering program. I went there for undergrad. I really liked engineering. Like, I originally wanted to go there and get in and out as painlessly as possible just to get a degree and go get a job at some local factory. But it turns out I was pretty good at it and I really liked it. So I went off to grad school. I got an NSF Graduate Research Fellowship and a DoD Smart Scholarship to help pay for grad school. And I got my MS and PhD down at University of Florida. After that, I went up and I worked for 3 years at the Air Force Research Lab. I was officially in the Sensors Directorate, but the last year I was there, I also worked with the Aerospace Systems Directorate quite a bit as well. I originally went to grad school because I wanted to be a professor. I really enjoyed my experience at U of E. It's a teaching school. I had great professors, and I was like, hey, I want to do this. This sounds like a pretty sweet gig. And then, I started doing research. I really liked research too, but I always kind of wanted to get back into academia. So thankfully, a position opened up across the street over at Wright State University while I was working at AFRL. And I applied to it, and they gave it to me, which was nice. And I taught for 3 years at Wright State, and I really enjoyed it there as well. It was great, actually. And I was pretty happy with moving back to academia. And then I started talking to a few people down here at UC, and they made me a really sweet offer. So I came down here, and I've been here since about 2018. So that's how I got here. If anyone has any questions about potentially going to grad school, because I'm assuming a lot of you guys may be undergrads, if you're interested in going to grad school, you should definitely look into some of these big fellowships. So like the NSF Graduate Research Fellow and the DoD Smart Scholarship. These are great opportunities to get paid pretty well to go to school. Like when I went to grad school and I had the NSF Graduate Research Fellowship, which was, a little ways ago, it was like 10 years ago. They pay all your tuition for 3 years, and they give you a $30,000 a year stipend. So that's $30,000 a year cash in your pocket. And all you have to do is go to school, and there's like no obligation. It's a pretty sweet gig. So everyone should look into that. And if you have any questions, shoot me an email. I'd be more than happy to talk to anyone about that. So now my research. So I do control and sensing again in adversarial systems. in particular, I do a type of control, mostly called game theoretic control. So I'll talk about more what that means here in a second. But basically, we're trying to design trajectories and control strategies for mobile agents. These may be sensing platforms. These maybe we have to select different types of behaviors for these mobile agents, and maybe we have teams of agents. So we're actually trying to coordinate behaviors within the team. We do kind of more generic type autonomous robotics stuff where we use machine learning, more traditional trajectory optimization methods. And then we actually try to implement some of the stuff and validate that it actually works in real life. And then the last thing I do, which I don't publish much on, partly because it gets a little hairy, is deception within adversarial environments. So how do we actually model the concepts of deception? Like, what is deception? Can you develop a mathematical model for deception? Can you develop a mathematical model for an intent? So there's some agent out there, he has a goal. How do we model that goal? How do we model what he's actually trying to achieve? And can we estimate that from his actions? And can we estimate it from his actions if he's trying to trick us into making us think he's doing something else? So it's really interesting. I do have a research lab. This is actually a picture of my old lab at Wright State. But basically, by the time I got my lab set up here, COVID hit. So we haven't had any parties in my lab here yet. Hopefully, once COVID gets better, we'll start doing little game nights. We used to have game nights in my lab. We play like Magic cards or board games or something like that. Currently, I have 5 PhD students working in my lab. I've had several former students that I've graduated over the years, and I'm kind of always looking for the next student to get in the pipeline. So if any of this stuff sounds interesting to you guys, shoot me up and we can talk about it some more. So what is game theory? So game theory has an unfortunate name in the sense that when you say you do game theory, people think that you're talking about playing video games or card games or board games or something like that. And although that can be an application for game theory, you can absolutely apply game theory to those scenarios. Game theory is really the study of conflict of interest. So it's competition often in the information domain between players who each have their own goal. So in this kind of cartoony representation, we have player 1. He has some value function that he's trying to optimize, and this value function is dependent upon the environment in some way. And player 1 can get information. Actually, I'll point. I think you guys can see my mouse here. Player 1 can get information through sensing from this environment, and then he can influence the environment through his control, U1. But at the same time, there's other players, in this case player 2, who also have their own goal that's represented by a value function. They can get their own information through some kind of sensing network, and then they have their own control to manipulate the environment as well. So they're both trying to manipulate the environment at the same time to achieve their respective goals. So we want to know what the optimal way for each of these players is to behave. However, that optimal, the best decisions they can make are dependent potentially on the decisions that other players make. So when we say things like, oh, what's the optimal strategy? It's really what's the equilibrium strategy, because it's not just optimal in a vacuum. It's optimal taking into account other players' actions. There's actually many different types of equilibrium. There's like Nash equilibrium, Stackelberg equilibrium. Most of the time, what we're going to talk about, at least I'm going to talk about in this presentation, is a Nash equilibrium. And the nice thing is that gives you a worst case guaranteed bound on performance. So no matter what the opponents implement, if you implement your Nash equilibrium strategy, you're guaranteed a certain level of performance. And this is a really strong concept, right? You can go out in the world and you can say, this is the strategy I'm going to implement. And no matter what anyone else does, I know that I'm going to get a certain level of performance. And in fact, if they do something that's non-equilibrium from their perspective, and may even get better performance. So every game has these kind of core components. There's players, so these are the agents that have to make decisions. It could be a person, it could be a machine like a robot or autonomous system. It could even be nature. We can model nature or noise even as an adversary in some of these scenarios. All these agents, all these players have utility functions, and this captures their desires. It tells us how they're hoping to achieve, or what they're hoping to achieve, right? What is their goal? If you think about, a card game perspective, it could be the expected payoff of a particular bet in a poker hand. Or maybe from a more military perspective, it's how much territory you can gain if you deploy assets in a particular region. Action sets are the possible choices that all these players make, right? So how can they influence that environment? What's their control on that system? From a poker example, you have a few choices. You can raise, you can match, you can fold, you can draw more cards. From this military perspective, you can hold assets in reserve, or you can deploy those assets to a particular front. Those are the decision spaces for that particular scenario that those players have to make. And when we define how these players make those strategies or those decisions by defining player strategies. So these are the mathematical representation of how players select actions from those action sets. And the form of those strategies varies depending on both the type of action set we're looking at and the type of environment or model we're using to represent that environment. And when we talk about solving this, when we say we're going to try to find the solutions to a game, what we're really talking about, again, is an equilibrium. So we're trying to solve for the best case strategy from each player's perspective, taking into account all the other players' best case strategies. If we're talking about one particular type, this is called a zero-sum Nash equilibrium. This is for a zero-sum game. So this is when player A is trying to maximize a particular utility function, and player B is trying to in this case, player A is trying to minimize a particular utility function, and player B is trying to maximize that same function. So their utilities are opposite in sign. So if you add them together, you get zero. That's where the zero sum comes from. And when we solve these types of games, we get a zero sum Nash equilibrium, and they satisfy this equation right here. And what this says is what I've kind of already said in words, is that if player A is trying to minimize, and we calculate his equilibrium strategy, call it A star. If he implements that strategy, he's guaranteed a value no greater than this equilibrium value. And from player B's perspective, if he implements this strategy, his Nash equilibrium strategy, since he's trying to maximize, he's guaranteed a value no less than this equilibrium value. So this equilibrium value is an upper bound from player A's perspective and a lower bound from player B's perspective, which is really powerful, and we can do a lot of really cool stuff with that. So, all of this has been pretty hand wavy. So I'm going to kind of present a really simple continuous game case. So suppose player A, his action set is to choose any real number. Like he can literally choose any number. Player B has the same action space. He gets to choose a real number. It's a zero-sum game, and the utility function is this xa squared minus xb squared. And player A is trying to minimize it, and player B is trying to maximize it. So xa, again, is player A's number that he's choosing, and xb is player B's number that he's choosing. Well, if player A is trying to minimize, he should choose 0. And if player B is trying to maximize, he should choose 0. So actually 0, 0 is the equilibrium control strategy for each of those. And the equilibrium value is 0. And if you would plot this in a 3D plot here, where this axis is player A's choice, this axis is player B's choice, and the z-axis is the utility, you'll see that this 0, 0 lives in a saddle point. This is the equilibrium point of this function. So these are also called saddle point solutions. And you'd say, okay, that's kind of interesting, but this game seems kind of pointless. Like, why would we need to ever do this? Well, this is just a really, really simple example. And in fact, what we do is we actually solve not for single values, We solve for entire control trajectories. So we solve for control strategies that are actually functions of time. So that action space is no longer just a single number, it's an entire function. And we're trying to solve for that function of time over the possible space of all functions of time. So we have to use things like calculus of variations. I'm not going to go into all those details in this presentation because one, it's boring. It's not boring, but it's involved and it's it's a little heavy for this type of presentation. So I'm going to give you some examples of some of the problems we solved. I'll gloss over some of the calculus of variations, but these problems illustrate what we're trying to do. So suppose we have a motivating scenario here, and it's like we call it a high value kind of target protection, or like maybe it's like an embassy protection, base protection type problem. There's people out front who are upset and they want to tear things down for whatever reason. And our goal is to decide how to protect these high value assets. So player A is an attacking force. They want to bust in, tear stuff up, but they have two choices. Like they don't want to go in and tear stuff up if there's a risk that they could be hurt, right? So they have to gauge that risk. Is it worth going in to engage the target, or is it worth just going home and worrying about it another day? Player B is defending. He's defending the gate, and he has to choose whether to direct fire on the attacking force or hold his fire. So he doesn't actually get any benefit from harming anyone. Like, they don't want to harm anyone. They just want to make sure that their stuff doesn't get torn up. So they have to decide their rules of engagement. And we can represent this scenario mathematically. So player A, his position, he's just a mobile agent. He's running around out here. We define his position using Cartesian coordinates, X and Y. We define the position of the high value target at the origin, 0, 0. And we say that this target successfully engages the attacker successfully engages the target when he comes within some capture distance of that target. So if he comes over here and he gets within distance DC, which is satisfied by this equation down here, we say he successfully engaged the target. Or if he wants to retreat, he can come down here and cross this retreat boundary, which is satisfied with this equation. We model his motion with the set of differential equations, these dynamics, and he has an integral cost. So this integral cost is actually dependent upon the control of the defender. So this instantaneous cost here. So the defender, again, can basically choose to shoot at him or hold his fire. So the defender can't prevent him from engaging the target. He can only try to manipulate the attacker's choice through a manipulation of cost. And if the attacker ends the engagement, he gets a bonus. Sorry, if he ends the game in engagement, he gets a bonus value. If he ends the game in retreat, he doesn't get a bonus value. From the defender's perspective, if the attacker ends the game in engagement, he gets a penalty. And if he ends the engagement in retreat, he doesn't get the penalty. So the defender wants him to retreat, so he doesn't get a penalty. The attacker wants to end an engagement, so he gets a reward. But if that reward is offset by too much cost, if this integral term is too negative, it may just be better to retreat. So how do we solve this? Well, we've done a bunch of math. We've written a few papers on it. If you're interested, you can go look up those papers. But basically, there's a 3-step solution. So we solve one problem where we assume the attacker will always engage, and the defender is going to minimize his utility. So he's going to shoot at him, basically. We solve that. Then we can use that value function to pose another problem where we assume the attacker retreats, and we assume the defender cooperates with the attacker. And if we can do that, so along the entire path, it's always better to retreat, then it's actually best for him to retreat. If we can't solve a path for that, it's better for him to engage. And if we can't or can, it divides the admissible state space into these two regions, a region of retreat and a region of engagement. And then we can create an equilibrium solution based on those divisions. So step one, we solve for a game of engagement. If any of you have done any kind of optimal control, that's very similar to how we solve these problems. Create a Hamiltonian, we maximize, minimize that Hamiltonian, we get some adjoint equations, create a 2-point boundary value problem, and solve it. And if we do that, we get a solution that looks like this. So wherever you start, the best way to engage the target is intuitive. You go straight there. So you run straight to the target. And the whole time the defender's shooting at you. So you want to get there as quickly as possible. Ends up straight lines. Again, it's intuitive, but we can mathematically show that all these straight lines give you the best utility. And this function on the right is what we call the value function. So wherever you started and you run there and get that bonus minus the cost, this is the value that you would receive. So this is the target here. And as you get further and further away, the value is less and less because you're racking up a lot of negative costs to get there along the way. If we have multiple targets, you can solve that case, and then you have to decide which target to engage. We get these things called dispersal surfaces. We can generalize it, but this is what those solutions look like. And then you'd say, okay, well, if the defender wants this guy to go away, he should just like always shoot at him, right? Well, maybe not. So suppose that the attacker, again, has the option of retreating. And suppose that the defender is always going to shoot at him. Well, if we assume the defender is always going to shoot, this is the optimal response from the attacker. So if he starts below this black line, he should retreat and end the game as quickly as possible, and he won't get a reward. If he starts above the line, he should attack in the game and engagement, and he gets the reward. But basically anything up here, he should attack, because if he runs down here to retreat, potentially it's a longer path and he doesn't get the reward. So he has no incentive of retreating. So you may as well end it in engagement. But what if we let the defender make an agreement with the attacker? And he says, hey, look, man, like, I know you want this reward, but I don't really want to take the penalty. And if you agree to retreat, I won't shoot at you. So just go home. I won't shoot. And you don't get that really expensive cost. And that's good. Like, you don't get your reward, but you don't get a whole bunch of cost. So we can actually make that agreement and make retreat more attractive than engagement, while you're getting shot at, basically. However, you can't do this naively. So if he would start up here at this position, and we'd make this agreement and say, hey, look, actually, we're going to hold our fire and we're going to let you retreat. While he's retreating, he's coming down this line, he's actually going to get really close to the target. And he's going to say, hey, look, I'm actually in a pretty good position. I'm just going to switch to engagement now, because even if you shoot at me after I switch, I'm still not going to incur that much cost because you didn't shoot at me this whole path up here. I'm going to switch. So the defender can't naively cooperate. So he actually has to escort the target around. So we can do a bunch of math and we can create these constraints that says, yeah, you can retreat, but you can never move into a region where it gets better for you to switch to engagement. And if you do that, we get these constrained trajectories. We call them escort trajectories. And you can see, like, he starts up here, he retreats, and he has to move around this region so he doesn't get into a better region of engagement. And when you solve that, you get a solution that looks like this. And we can compare this. So over here is when he always shoots. Over here is when he selectively holds his fire. And he says, yeah, you can retreat, but you have to retreat around the target. So we've converted all this region up here that was engagement only to now retreat through strategic cooperation with the enemy. And that's what game theory does. It helps you achieve your goals while taking into account and potentially manipulating the goals of other players. And this is why it's a big benefit. We can compare the value functions between those two solutions as well. And we see that the attacker is still actually getting a better value now. So even though he's retreating, this is retreat region here, he's still getting a better value than when he engaged and got shot at the whole time. So everyone wins, actually. And we can extend this to 2 targets. I'm not going to go through the details, but we start getting solutions like this. So this is a target and this is a target. You start getting multiple constrained trajectories and it can get pretty complicated, but it makes for a nice research project. All right, and we can extend this concept to all kinds of different applications. So we can have multiple targets. We can have mobile targets. We can start doing things like target selection. There's cooperative control problems. So you may have a high value target and a mobile defender who can intercept the attacker. You try to intercept them as far away as possible. Oh, I think we have videos on this one. We have like turret-based problems. So this guy's trying to come in and attack. This is a turret that's trying to swing around and intercept him before he can attack. We have like integral cost. We can also pose them as sensing problems where we have targets who are or attackers who aren't necessarily attacking to destroy, they're trying to collect information. And we have these targets moving around to avoid the collection of that information. And these problems can get really complicated, and so complicated that some of the traditional analytic methods kind of break down. They don't scale well. So another branch of what we do in my lab is actually using machine learning to solve it. This is one example of where we did that. Basically, we're trying to develop dogfighting strategies using evolutionary algorithms. So each player has a heading. They drive around on a 2D plane. We can define the system using a relative coordinate system to reduce the dimensionality of the problem. And then we created this anchor point method where basically we put these things called anchor points that have a control associated with them in the state space. And we look up wherever we are in the state space, find the nearest anchor point and implement that control. And we just represent the controller as a collection of these anchor points. And then we can use an evolutionary algorithm to actually evolve where those anchor points are. And then we dogfight them. So we actually create a whole bunch of random controllers. We dogfight them all, pick the best ones, breed them together, add a little bit of random noise, and do that over many, many generations. And we'll get better and better controllers. And that's how an evolutionary algorithm works. So we have some really nice computers with lots and lots of cores, and we just run parallel simulations of dogfights over and over and over. And we get things that do this. So let's see, player A is one of our EA evolved controllers. Player B, the red one, is just a benchmark controller. So basically, we made a dummy controller where this guy always tries to turn into player A. Now, it's important to note that this scenario doesn't end if they meet head on. So it only ends if one of the players can get behind the tail end and get within the capture distance of the other player. So you have to get behind him and within weapon range to end the scenario. So on the left is the 2D simulation of how they look out just driving around. And on the right is our relative coordinate representation of the scenario. So you can see which anchor point is activated as it moves through this relative state space. So the green's left turn, the circles go straight, and the red is right turn. And you can see he actually caught him from behind. We also try to validate this in hardware. So we had this little test bed. We can drive these little robots around. We can run some of them autonomously using our developed controllers, and then we can run other ones manually with like an Xbox controller and dogfight basically. That's my son. That's like 2 years ago, and he was driving the little robots around and dogfighting them. So I actually had a master student design these robots, these little puck robots, and we have a camera up above that does all the motion tracking and feeds that information to the computer right here that calculates all the control and then pipes the control wirelessly back to each of the robots. So another thing that we're doing is actually using pinball as a test case for these methods as well, because actually pinball has a lot of similar characteristics that you may find in a real system. It's chaotic, it's highly nonlinear, and you actually have to design, or well, not design, but you have to make decisions. There's a risk-reward analysis when you decide which shots you want to shoot. So we're actually using our machine learning algorithms to learn how to play pinball. And then we just hook up a computer to flip the flippers, and we have a camera up above to do all the motion tracking, which is one of the feats right here. And the cool thing is Stern Pinball is it's like a legit real world pinball company, has given us like thousands and thousands and thousands of dollars in hardware. So in this picture here on the left, all these play fields were actually donated by Stern Pinball. So now we can take parts off of those and build test play fields both for our research and for senior projects and for courses. So like I'm doing a mechatronics course, which I actually designed a custom pinball machine for for that course. Unfortunately, I'm not sure if we're going to get to use it this semester because we're all locked away for COVID. I'm hoping to figure out a way of getting people in the lab, at least maybe individually and in a limited basis, so that they can learn how to program these pinball machines. So yeah, I basically built this at the end of last spring semester for my mechatronics course. It has a lot of cool stuff. We designed like custom PC, or I designed custom PCBs that have all the different pieces and parts that you'll learn about in the mechatronics course. The play field has a lot of different actuators and sensors that we're going to talk about in my mechatronics course. We have a stepper motor, we have a servo motor, we have a DC motor, we have quadrature encoders. There's actually a proximity sensor that we can mount on this piece. Then we talk about the control state machine for the flipper mechanisms and the pop bumpers, and as well as the rule state machine for the pinball machine itself, which is pretty cool. I really hope we're going to get to use it, but we'll see. And let's see. I think that's it. So I think I'm right around 30 minutes. So I was trying not to take too long. But if there's any questions, we can definitely go back and talk about anything that you guys want. So thanks.
Awesome. Thank you. Yeah, if there are any questions, feel free to ask in the chat or unmute yourself. But that is very cool and above my head a little bit with the math. But we did a lot of very similar calculations, and it looked like problems in my quantum computing class I took last semester, which I thought was really interesting. But yeah, cool. It's awesome.
Thanks. So if anybody wants to play,
question.
Oh yeah, go ahead.
Yeah. So how, for any undergraduate students here, how early would you recommend them kind of thinking about the graduate level path and kind of looking into the options there? And when would you say is maybe too late or?
Well, it's never too late. That's one thing. So it's never too late, but it's also never too early. So for example, I mentioned I had the NSF Graduate Research Fellowship. And the reason that I guess learned of it is actually I was IEEE president as well, student president back when I was in undergrad. But we also had, like, I was a member of IEEE before that. And, every year, it was usually, I guess, early in fall semester, our department chair would come and give a presentation to the IEEE student chapter about grad school. And that was particularly important for our school because we didn't have a graduate program. We were only an undergraduate university. So most of us had little to no exposure to anything graduate related. And he basically went through and was like, hey, look, engineers are in a unique position because most of us can get paid to go to grad school. The vast majority of engineering graduate students get some kind of support. It may just be tuition support. Maybe you can get a teaching assistantship, or maybe you can get a research assistantship. And there's these other really incredible external fellowships, like the like the NSF Graduate Research Fellowship, and these DoD type fellowships and scholarships. And I learned about it my sophomore year, and it was like I never knew that you could get paid to go to school, because at the time, and actually all through my undergraduate career, I worked at a farm supply store to pay for school. So I was working like 30 something hours a week at a Rural King. I don't know if we have Rural Kings around here, but it's like a tractor supply store. I was working like between 30 and 40 hours a week and taking 18 to 21 credit hours because I was going to dual major in mechanical engineering, which I eventually just got a math minor instead. But and I was like, wait, like I can get paid to go to grad school and I don't have to work like crazy number of hours to do this as well. And I went and talked to him, and he's like, look, here's the things you need to do to position yourself as best as you can to try to get that fellowship. And I was like, yeah, okay, I'm sold. So I spent it's not that I was trying to game the system, but I was trying to put together as best I could an application. And I spent basically 2 years of my life doing everything I could to make myself the best applicant I could for that NSF fellowship. So things like heavy involvement with my IEEE chapter. You know, I became president of the IEEE chapter, and I organized a lot of outreach activities. So like I organized these trips to the local children's museum where we did like science and engineering days and had like hands-on activities for all the kids and stuff, which actually like I really enjoyed anyways, partly why I'm a teacher. But like that's the kind of stuff that say NSF likes to see. I was the president of Eta Kappa Nu. I did undergraduate research projects, and that's an opportunity that a lot of you have being at a university that already has research involved. And that's also a good way to figure out if that's even what you want to do. So you can approach different faculty in areas that you're genuinely interested in and say like, hey, like, is there something I can do? Like, is there something I can do to help out in the lab? Like, just to get my foot in the door, just to like hang out and see like what people are working on and see if this is something that I might want to do. And then maybe you can do a little project. Maybe you can get even a little paper published, or you can do a little project and submit it to our student magazine. You know, that's another nice thing that we have going for our department, is that we have a student magazine. So it's not as nice as like a peer-reviewed journal or anything, but it gives you an outlet to talk about the stuff you've done. And then once it's out there, you can point to it, right? If you go talk to some other faculty member, you can point to that article and say, hey, this is what I did. Even if you go out and get a job, you can point to that article and say, hey, this is what I did. So I would say, like, if you are even remotely interested in grad school, like sophomore year, start thinking about like what you need to do to kind of make yourself to position yourself the best you can at the end of your undergraduate, and when you're starting to apply for things like external fellowships and graduate positions, either at UC or other universities. And the good thing is, like, even if you decide not to go to grad school, those are still the same types of things that employers want to see too. So yeah, I would say like it's really never too early, and it's never too late. Because I mean, you know, I've had grad students who thought they were going to go get jobs somewhere, and they went and interviewed places, and they're like, you know, like these are okay, but really, I want to do slightly more advanced things. So maybe I'm going to stick around and get a master's degree to open those doors. One thing I will definitely advise against is graduate school is not a good option if you just don't want to go get a job. Like sometimes people are like, oh, I don't want to go get a job yet. I'll just do grad school and I don't have to worry about like finding a job. That's not really the right reason to do graduate school. Like you should go to graduate school because it enables you to do something else that you want, right? Like I wanted to be a faculty member eventually. You have to have a PhD to do that. Like, so I went to grad school to open those doors. Along the way, opened a bunch of other doors, and I got to go work at the research lab and stuff like that. But I originally went to grad school with a goal, an end goal in mind. And maybe you just want to do more like design centric work in a certain area, and a master's degree would be actually really beneficial for that. So, you know, it opens doors, but you have to make sure those are doors that you actually want to open, because it's not easy. It's a lot of work. So, sorry, I think that was a long rambling answer to your question, but it's a good question.
Yep, very valuable. Thank you.